Hello, hello, hello. This is Nicholas on this lovely Tuesday morning, and I have a quick prerequisite video for you on the next video that I'm going to make, which will be proving that the Fibonacci sequence is a strong divisibility sequence. But in order to do that, I have to give some background on what's called the Euclidean algorithm, and this is just an easy way to determine the greatest common divisor of two numbers. So the Euclidean algorithm basically says that, let's say we have A and B natural numbers, and we repeatedly perform the division algorithm. Now, you might not have heard it called the name by the division algorithm, but basically the idea is division algorithm, we have something, take, for example, 27. It can be written in the form 3 times 7 plus 6. And so the division algorithm says that if we have a number A, it's going to go Q times into the divisor B and leave a remainder of R. Right? And that's the basic notion of divisibility in like elementary school. Maybe they didn't say it that way, but that is what they were getting at. Now, so we repeatedly perform that division algorithm. So in other words, we say A is equal to, say, B Q sub 1 plus R sub 1. And then we would set B equal to R sub 1 Q sub 2 plus R sub 2. And then we'd have R sub 1 equal to R sub 2 Q sub 3 plus R sub 3, dot, dot, dot. And then we would have R sub n minus 3 being R sub n minus 2 Q sub n minus 1 it would be, plus R sub n minus 1. And I'm almost done here. We'd have R sub n minus 2 being equal to R sub n minus 1 Q sub n plus 0. Eventually, what we're saying is that the remainder is going to get down to 0. And we would say that on the nth remainder that we're eventually going to get down to 0. Because these are just finite natural numbers, eventually we're going to get down to 0. And this is going to make sense later on when we do an example. And then what we say then is that R sub n minus 1 is going to be then the greatest common divisor of A and B. And now the proof really is not that bad. See, first thing we got to notice is that the sequence of remainders, in other words, R sub 1, R sub 2, dot, 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 up to somewhere. In other words, and we call that the nth remainder, we said, in other words, somewhere, the remainders, and every element of this set is a subset of the set of natural numbers, so it's a subset of n. These remainders are decreasing. And so if they're decreasing, then by what's known as the well-ordering principle, it's got to truncate. It's got to end somewhere. And it's going to end, we say, at the nth remainder, because these are finite numbers. So the set truncates at some point. And so therefore we are actually there. In other words, this part of the proof implies the existence of this 0 right here. Now, what we're going to do now is we're going to show that R sub n minus 1 divides A and divides B. In other words, we're going to show that R sub n minus 1 divides A and R sub n minus 1 divides B. In other words, we're going to show that R sub n minus 1 is a common divisor of A and B. And then we're going to show that R sub n minus 1 is the greatest such common divisor. So how we can do that is actually kind of cool. See, I know from this equation right here, by the definition of divisibility, that R sub n minus 1 divides R sub n minus 2. But then I know that if R sub n minus 1 divides R sub n minus 2, and if I look at this here, I could replace this R sub n minus 1 with, say, Q q prime r sub n minus 2. In other words, I'd have an r sub n minus 2 and an r sub n minus 2. And then so I'd have r sub n minus 2 as a common factor. And so this implies that r sub n minus 2 divides r sub n minus 3. But division has this transitivity, and so therefore r sub n minus 1 divides r sub n minus 3. And then I could continue up and up and up, right? Up and up and up, eventually to the point where I get that r sub n minus 1 divides b, which implies that r sub n minus 1 divides a. And so r sub n minus 1, therefore, is a common factor of a and b. Now, the very last thing that we need to do is prove that it's the greatest such common divisor. So basically what we're going to do is we're going to show that, let's suppose that d, the greatest common divisor, so let's suppose that d, the greatest common divisor, d divides a and d divides b. And we're going to show that d has to be equal to r sub n minus 1. So what I'm going to do now is I'm going to say, well, okay, if d divides a and d divides b, then d divides any linear combination of a and b. So namely, d divides a, and then what I'm going to do is I'm going to look back up here. It's going to divide a minus, all right, and actually for right now I'll write it as plus negative q sub 1b. So in other words, if I look at this right here, d divides a and d divides b, then it divides the linear combination of 1a plus negative q sub 1b, right? This is a linear combination of a and b, and so therefore d divides it. But if you notice, a minus b q sub 1 is equal to r sub 1, right? From this equation right here. And so therefore, d divides r sub 1. Now, if d divides r sub 1, and you see it's kind of recursive here. If d divides r sub 1, then d divides, what it's going to be, d divides r sub 1, and d divides b, then d divides any linear combination of b and r sub 1. So namely, d is going to divide b plus negative q sub 2 r sub 1. But if we look up here, b minus r sub 1 q sub 2 is equal to r sub 2. And so therefore, d divides r sub 2. And we can continue going down like this, so on, up to the point that we're going to get, after so many iterations of this, we're going to get that d divides r n minus 1, the last non-zero remainder. And so if d divides r sub n minus 1, and d is the greatest such common divisor, then that implies that d is equal to r sub n minus 1. In other words, the greatest common divisor of a and b, which we define to be d, is r sub n minus 1. And so that's the proof. Now, I think it will make a bit more sense here to do just a quick example. And so let's do just that here. I'm going to come up with two random numbers here, and we're going to calculate the GCD of those two numbers. That's the whole point of the Euclidean algorithm. So let's say I want the GCD of, let's say, 5295 and 4321. All right. So basically, the idea is we're gonna proceed like this. We're gonna say 5295 is going to be equal to 1 times 4321 plus 974. Okay, so I've broken it up into, I've broken A up into B times Q plus a remainder. Now I'm going to break up B, which is this 4321, into multiples of 974. So 4321 is going to be equal to, I believe that's 4 times 974 plus 425. And now I've broken up 431 into multiples of 974 plus a remainder of 425. Now I'm going to break up 974 into multiples of 425 plus a remainder. And so 974 is 2 times 425 plus a remainder of 124. I now break up 425 into multiples of 124, and that's, let's see, what would that be? 425 is 3 times 124 plus 53, and now I keep going, right? So 124 is equal to 2 times 53 plus 18. 53 is equal to 2 times 18 plus 17. And then 18 is equal to 1 times 17 plus 1. And then we're obvious, it should be obvious that we're going to stop right here. 17 is equal to 17 times 1 plus 0. And so what that tells us here, we look at the last non-zero remainder. That last non-zero remainder is 1. And so that tells us that the GCD of these two numbers is equal to 1. In other words, they're relatively prime. They share no common factors. And we're done.